Hey, everybody. So I'm in the middle of grading the second exam, and I noticed that the last problem seemed to be the one that was causing the most consistent trouble. So I wanted to make a quick video, explain it to everybody. It's I think an interesting enough problem, and if you look at it right, it actually ends up being not as difficult as we may have made it out to be. So the first thing to do is understand the situation, right? We're given this plane, x minus y minus z minus 8 is equal to 0. And this point P, 1, 0, 1, which is not in the plane, right? It's quick enough to see that it's not in the plane. And we want to know what point in the plane is closest to this point. A lot of people answered this question by just telling me the distance from this point to the plane, which doesn't answer the question, right? We want to know what of every point in that plane is some distance from this point P, and we want to know which one of those has the smallest distance, right? And the intuition I want us to get here is as follows. So just a quick sketch. So here's my plane, just some arbitrary plane. Right, x minus y minus z minus 8 is equal to 0. And there's a point off of the plane. I've named my point P. And I want to know the closest point in the plane to this, right? So how do we decide closeness, or what's the closest one? And we could write some the distance from this point to any point in the plane, and then try to minimize that with the constraint of the plane. And that's is a problem that's doable, but not simple. And there's actually a nice intuition that will make this really simple. Point right now, wherever you're watching this, to the nearest wall. Point at the place on the wall, the point on the wall that's the closest to you. And I imagine most of us are pointing in a way that if you extend a line from your finger to the wall you're pointing at, that line's going to hit it perpendicularly. And that's the correct intuition, right? And it's a simple enough idea to prove, even like in a quick proof sort of way. If I imagine drawing a line that hits this plane such that it's perpendicular, if I choose any other point on the plane and draw a line to it, whoops, right? You can imagine forming this triangle, which is going to be a right triangle, because we already said that the line that we've drawn to this point that we're calling the closest is perpendicular. And so there's a right triangle there. This angle over here is not perpendicular, neither is this one. And we can form this triangle, and the distance from P to this other point is the hypotenuse of that right triangle, which is necessarily longer than this perpendicular line. And so that's a quick kind of geometric, let's call it an intuitive proof that the perpendicular line is the closest. This gives us a nice strategy for this problem. We want to, what we can do is figure out the equation for the line. Let's erase some of this to make this a little easier to look at. Don't need this anymore. We can find out the equation of this line. There's the line continuing on through the plane, right? This is the line that goes through point P and intersects the plane orthogonally. It's perpendicular to the plane, okay? Well, we know for a plane a direction that's perpendicular, the normal vector. The normal vector to this plane, remember, we can read straight from the equation. It's simply the coefficients of x, y, and z. Oops, not negative z. The coefficient of z, negative 1. All right, so there's a vector here that I've just named n. It's their normal vector, right? It's perpendicular to the plane, right? And that is what we can use as the direction vector for our line, this line that I want to find. I'm going to call the line L of t. So remember, for our lines, what I need is a vector pointing at a point in the plane, and then a direction vector, which I've already got as n. And I already have one point in the plane. It's this point P. So a vector pointing at point P will have components 1, 0, 1. And then we have T times 1, negative 1, negative 1. And I'm going to write this, in a little more convenient of a form, at least for what I want to do. I've got 1 plus T, I've got negative T, and then I'll have 1 minus T, right? So here's an equation of the line that goes through this point P and intersects the plane perpendicularly. So we want to know where this line intersects the plane, right? Well, I know that this is the x coordinate of this line, this is the y coordinate of this line, and this is the z coordinate of this line. When it intersects the plane, what that means is that there's a value of t that when I plug it in, the x, y, and z coordinates that get spit out satisfy the plane equation. In other words, we would need to have x of t minus y of t minus z of t minus 8 equals 0. When that's true, whatever t value makes this true, then the point that's being spit out is on the plane. Since it's on this line, it's perpendicular to the point P, which means it's the point we're looking for. So let's solve this equation. Let's come over here where I've got a little more room. And we've got, so x of t is 1 plus t minus y of t, so that's minus negative t, minus z of t, so that's minus 1 minus t, minus 8 is equal to 0. So let's just solve for t. So I'll collect the t's. I see I have a t, a plus t, and I'll have another plus t. So I'm going to have 3t. Well, I'll have an 8. I'm going to add that to the other side. There's this 1 here, and I'll get a negative 1 here. So those two things will cancel out, right? There's a 1 right here and a negative 1 right here. Once we distribute that negative, those will go away. So I've got 3t equals 8, or t is equal to 8/3. Right? So now I know the t value that gives me the point that I want. I can plug this back into our equations. So x of 8/3 is 1, or 3/3 plus 8/3 gives me 11/3. Y of 8/3 is negative 8/3. And z of 8/3 is 1 minus 8/3, so negative 5/3. And so the point in question is, where am I? There we go. 11/3, 8/3, negative 8/3, and negative 5/3. Okay. And you can go ahead and check. Well, it's quick enough to check. Add these up, and we get 24/3, or 8, when we plug that into our equation, x minus y minus z. Sorry, I said add these up. I meant take x minus y minus z, 11/3 minus negative 8/3 minus negative 5/3 gives us 24/3, minus 8 gives us 0. So we know this is a point in the plane, and it's on this line that we know is perpendicular. So this has to be the closest point. Closest point to P in the plane is this point here. All right, let's take one quick look at a nicer graph of this whole thing. So here is our plane. Okay. Here is that point I called P. The computer automatically named it A. So we see it's not a point on the plane. Here's the line that we found that's perpendicular. Uh-oh, I've lost the edge, so it's controlling this in a weird way. I don't know how to get back. There we go. There we go. In fact, let's get the, yeah, just got the axes out of there. They're not really helping us understand this. So there's our plane, there's the point we wanted, and there's a line perpendicular to the plane through that point. And here's that point we just found that it has labeled B. which has the coordinates 11 thirds, negative 8 thirds, 5 thirds, negative 5 thirds, right? And it does seem to be, intuitively looking at this plane, what we imagine the closest point to be. It's a little hard to see. I know it's not always easy to tell what we're looking at with these graphics, but it's as good as I can do. Okay, that is it for this. Thanks, everybody. I will talk to you next time.